Hello, welcome to week 1. This is going to be about limits. Okay, first I'm going to show you an animation here I created using something called Manim to talk about limits. Okay, so let's say we have this function. On the left there, on top, is x squared minus 1 over x minus 1. So the idea of a limit is that when x, we look at the function and as we get closer and closer to x being 1, we want to know what happened to y. And there are two ways to approach 1. We can either approach 1 from the left side, this is the yellow dot here, and that's on top, left, or we can approach 1 from the right side. This is x approach 1 plus means from the right side. And if I play the animation, you notice that the y value, right, you look up here, the y value for both going from the left and from the right is approaching 0.5. There it is. So it's converging towards 0.5. So let me kind of play that again. Here it is, right? So the idea of a limit is exactly this, is that as x approaches 1 from either side, does the function approach the same value? And in this case, it does. It both approaches 0.5. And so that's what a limit is. We say that the limit as x approaches 1 of this function is 0.5. And notice that this function actually have a hole at 1. In other words, f of 1 is undefined. So even though the function is undefined at 1, the limit still exists at 1, and the limit is equal to 0.5, again, even though there's a hole at 0.5. There it is again. And notice if I zoom in here, right, that there is that hole there. So again, the function can be undefined, but can still have a limit. This kind of I want to kind of show you 3 cases here that comes up. The first case is where the function is continuous. You may remember from pre-calculus. Function is continuous if you can draw it without lifting your pen or pencil. And so let's look at the one on the left. And notice that it has that we're going to approach from both sides here, and the limits here is going to be 2. And now let's look at the case on the in the middle. This is a case where there's a hole in the middle, and so even though there's a hole, the limit is still 2. Right? As I approach from both sides, right, the y value is approaching 2. And then the last case is the case on the right here. Notice that there's not only a hole there, but the function is the function here is actually defined there, but the function definition is actually different than the hole. So the value jump. But even in this case, notice when x approaches 1, the limit still approaches 2. So in all 3 cases, we do have that the limit is 2, even though all 3 cases are slightly different. So here's another example. If I were to look at this function, sine of x over x, notice if I plug in 0, is 0 divided by 0? So the function is not defined at 0. When x is 0, there's a hole there. It's not defined. But notice if I plug in some points into the calculator, if I were to use the calculator, here's a table on the right. If you plug in plus or minus 1, I get 0.84. If I get closer and I plug in plus or minus 0.5, notice I get something closer to 1, 0.95, etc. If I get even closer, right, then I notice on my table 0.1, I get closer and closer to 1. So even though there's a hole there, right, we can verify with the calculator that the limit here is 1. So again, playing that again, as I approach from both sides, it's going to get closer and closer to 1, right? And again, even though the function is not defined at 0, you cannot plug in 0. The function is undefined at 0, but the limit exists, right? Zooming in, right? Notice here, the function is undefined, but the limit does exist and is equal to 1 in this case. And then that's the idea of one-sided limits as well. We saw that, right? So now this is a little bit different. Now notice on the left here, at axis 2, there's a jump there. And so I'm going to try to approach from both sides, right? From the left and from the right. Notice that if I go from the left side, the limit approaches 3, right? But if I approach from the right side of 2, the limit approaches 1. So notice that the one-sided limits are different in this example. The left-hand limit, the limit as actually approaches 2 with the minus sign, meaning from the left side, the limit is 3. But the limit as actually approaches 2 from the right side with the plus is 1. So the limit is different on either side. And so in this case, we want to say that basically the limit does not exist, right? Because the limit on the left and the limit on the right, they don't agree. So in this case, we want to say that the limit does not exist. This is the first case where we have a limit that does not exist. But we saw earlier, right? So we say that the limit DNE does not exist. But contrast to that, we saw this example earlier. The function is undefined. The function has a hole here, but it jumps down here. It is defined, but in this case, where the limit from both sides does converge to 2, so we say that this limit is 2, even though the function, right, has a jump there. Okay, let me go back to the slides. So again, right, the slides are posted, so please look at the slides. So we did a lot of this already with the animation. So this is from the textbook here. And so here's another case where the limit does not exist. This is the case where the function fluctuates forever. As x approaches 0, again, if you zoom in, this thing is going to keep fluctuating over and over again, from the left and also from the right. So this is another case where the limit does not exist by the fluctuation. Now, for most functions, if you have polynomials or rational function, and you plug in the x is 1, and you have a value, a well-defined value, in those cases, the function is nice. There's no jump, there's no hole, and so the limit in those cases is simply plug in the value that you want to approach. So in fact, this is kind of one of the first things we try. If you have a limit of a polynomial or a rational function, where when you plug it in and you get a value, then the limit is that value. So here the limit as x approaches 1 is 2. Here the limit as x approaches 1 is 1/3. We saw this example earlier in the animation. Is that the idea that there's a hole, but that limit exists. And so now I want to kind of do the algebra that justify that. Let's do that with the animation here. Okay, so how do I do this? Again, if I try to plug it in here, just like I get 0 on top, 0 at the bottom. And notice that's undefined. So this is a case where you cannot plug it in. If you plug it in and you get a value, then the limit is that value. But in this case, it's 0 over 0, so that does not work. So now we have to do some algebra to compute this limit. And notice on the top, we can factor the top out. So now the top is x minus 1, x plus 1, and the bottom is x minus 1. Now notice we can cancel this. And by the way, when you talk about the limit x approach 1 means that the limit never gets there, right? Remember, there could be a hole there, so you don't have to, the x never gets to 1, but we want to know when x gets closer to 1, what happens. Because x never gets to 1, the value of x minus 1 here is not 0. So this is why we can cancel, because if x was 1, you cannot cancel the 0. But because we're taking a limit, x is never 1, we can cancel. And then now we notice that we have something simple. Now we plug it in. And we get limit is 2. Here's another example. So first we do some algebra. We multiply everything out, and then we get this, and then we cancel the 9. So let me do that again slowly. So you multiply everything out, you cancel the 9, and then now we can factor out the h. And we can again cancel the h. H approaches 0, but it's never equals 0, so we can cancel the h. And then as the last step, we can finally plug in 0 for h and get the limit is 6. So that's how we do algebra to do these limits. And this is the case we saw a few times on the animation, right? Even though there's a jump here, the limit exists. The limit here is 2, even though there's a jump there. Here's another one. Notice that the previous one we just did was actually, notice that when you plug it in, you get 0 over 0. The case we did earlier here, we saw that when you plug it in, you get 0 over 0. And that's actually the most important case we'll see in this class, is when the limit is 0 over 0. And here's another one where it's the same thing. If you notice that when I plug it in, h is 0, you also get 0 over 0. And that's the case that's really most common. So we did that. We also saw one-sided limit earlier in the animation. For example, the limit on the left here is -1, but the limit on the right here is +1. Because the limits are different on those two sides, the one-sided limit is different, the limit does not exist. And then here's a case where the limit, as x approaches 0, notice that the function approaches infinity. It gets bigger and bigger, and it's going to keep getting bigger as you get closer and closer to 0. So this is the case where we have infinite limits. The limit here, you can say the limit here is infinity, or because infinity is not a number, sometimes you can say the limit here does not exist. But if you have to qualify how does it not exist, you can say that the limit does not exist, but it does approach infinity. And so that's called infinite limits. So again, does not exist is a valid answer, but sometimes we want to explain how it does not exist. In this case, the limit is approaching infinity. And this is the case where the limit approaches negative infinity. And these are called vertical asymptotes. And so these are different ways of getting vertical asymptotes. Notice on the left here, the limit approaches a on the left. See the minus there, right? That means you approach from the left side. That's an infinity. If I approach from the right side, see that's the plus. It approaches positive infinity as well. Here, if I approach from the left side, I get negative infinity. And here, if I approach from the right side, I get negative infinity. In all those cases, we have vertical asymptotes. This is the case where if I approach from the left, I get negative infinity. But if I approach from the right, positive infinity. So because of that, this is definitely a case where it does not exist, right? Because the two-sided limits are not the same. This is definitely does not exist. It has one-sided limits, negative infinity and positive infinity.